but hot afternoon. I welcome you in this session, which will be dedicated to the managing and monitoring of network resources. My name is Helmut Sverniak, I'm from CESNET, and in this session we will have three presentations. The first one will be held by Michal Bredl. Michal is professor at the University of Applied Science in Kufstein, Tyrol in Austria, and he is teaching and doing research in the area of network security and software development with the focus of software-defined networking, cloud computing and big data. His presentation will be held on the LACP implementation for open flow controller. Please, Michal, floor is yours.
So thank you very much for the kind introduction. And let's see. Yeah, perfectly, works. So welcome everyone to this presentation about LACP and OpenFlow. So this actually is joint work with a student of mine who did that work in his bachelor's thesis. So joint work means I'm presenting, he did all the hard work. And well, I'm working in that SDN area for quite some while now, and even today I still have this discussion, okay, what is SDN good for? What can I do with that? And this idea actually dates back to a conversation I had with a guy from Indiana University. And I'm trying to pick things like the neat things that you can do with SDN that makes life easier for you as a network manager, network operator, network guy. It's also, I'm not talking about the big networks on like ISP scale or NRN scale, but smaller networks like in your lab and things that you can do with SDN there that makes life easier. So for example, we run a testbed, not an SDN testbed, a general testbed with 4 switches, 4 top-of-the-rack switches, and an aggregation switch, and we use SDN to operate that network, which makes life much easier for us. So if you have a testbed, people tend to put new stuff in and take old stuff out and recable stuff and reconfigure stuff and bring up VMs and stuff like that. And that's basically, that drives you nuts, right? So your network configuration is changing all the time. And you need to go to the switches and configure VLANs and stuff like that. Using an SDN approach, that becomes much easier if you have a central point of configuration, for example. So that's what we do. Before I go into the technical part of the lecture, I used to work for CERN before in Caltech, and people know what CERN is, but I constantly hear the question, what's Kufstein? So this is CERN, and this is Kufstein. So it's a really small place in Austria next to the border to Germany, near Munich. And since yesterday we had a talk where someone showed some pictures from guys at the beach in Australia. In Austria, you can also do some interesting stuff, especially in the winter. We tend to go skiing there, and if you want to visit us, or even better, if you want to collaborate with us, just let me know. I just started there, and Kufstein does not have a big history on networking so far, but I'm building up the group, so I'm really looking for people who want to collaborate there. So the university itself has like 2,000 students, masters and bachelors, some professors, of course, and some external lecturers. We are really international. We have like 200 international students there every semester, basically. That's Kufstein. We're going to the technical details. So what am I going to talk about? Well, I want to talk briefly about how you connect servers to the network, really obvious, and how you can use an SDN approach to do link aggregation, doing that and avoid points of failure there. And I'm going to talk briefly about the implementation we did based on the Floodlight OpenFlow controller. And then I will show you some of the advantages of using that SDN approach instead of a classical approach of doing that. So what are the points of failures you have, right? Think about, you have a network, like a flat layer 2 network, some switches interconnected. Here you already have a forwarding loop, so you run spanning tree in that network, and it gives you some resiliency in the sense that if one switch goes down or one link goes down, the others are still connected. And you have a server that you want to connect to that network. So you just take a cable and plug it in, right? Where are the possible points of failure in that configuration? You see, I'm a professor, I'm asking you things. Hey. Well, there are actually several of them, right? So your server can go down, we are not dealing with that, you need a second server to avoid that, but your NIC can go down, or your SFP, or whatever you plug in there. The link itself, right, it can break, or it's more like the human factor, someone saying, oh, what's that cable for? I don't know, let's plug it out and see what happens. Or the switch can go down. What are you going to do to avoid that? Well, you install some redundant link, and that basically provides you the feature that link itself is not an issue anymore. If one link goes down, the other link is still up and running. However, you still have that switch, and if the switch goes down, your server still is disconnected. So, again, what are you going to do? Well, you install a second switch and connect your server to 2 switches instead of 1. Well, you can do that on layer 3 or layer 4 using MPTCP and stuff like that. We did that before as well. If you want to do it on layer 2, on an Ethernet level, you need to have a stacked switch, right? So you need to have a switch that can be interconnected in a specific way, and it's basically, it acts like one virtual switch in that sense. What's the problem? And you also need to connect these switches even more, so your network topology becomes more complex, basically. So that solves your problem, right? So if you have stackable switches, if you have a stacked switch, you connect your server to it, that's fine. It provides you scalability, it provides you flexibility, it provides you the high ability you may need. And that switch acts as a virtual switch chassis, so it's a virtual switch, basically. However, it also comes with some drawbacks, right? You need to have 2 switches, which increases your power demands, which increases the management stuff you need to do. Well, even the performance can be an issue. If you have more than 2 switches stacked, you need to connect them all the way through, and the link between these stacked switches can become the bottleneck. And it's kind of inflexible. Moreover, it's kind of expensive, right? You need to buy the specific switches, the special switches that are able to do that, and that's not the cheapest switches. So that's what was the discussion I had. Someone said, it would be really cool if I could do that with simple and cheap SDN switches instead of buying the expensive hardware from Cisco that in the end does still not really do what I want to do. And that's why we are looking into that using SDN. If you want to do link aggregation with OpenFlow, that's possible in general. But there are some challenges and things you have to think of. So first of all, you need to do it in a reactive way. So opposed to the proactive way where you install a flow before the traffic actually starts to flow. in reactive SDN, you react on packet in events. So whenever there's a new packet your switch does not know about, it sends this packet to the controller, and the controller needs to do some things with that packet. So that's reactive SDN. Well, you need to have some configuration management. That's kind of very obvious. Unfortunately, most of the research or experimental SDN controllers don't have that, so you need to create that, for example, in Floodlight. Then you need to have automatic link discovery using link layer discovery protocol. Most of the SDN controllers ship with that already, so it's there. You need to have the ability to perform multipath switching. So you need to be able to send the packets on different ways from a source to a destination. And we did that previously and also published some papers. I think we even presented that at TNC last year or the year before with SurfNet, for example. Ronald van der Poel was involved in that. So you need to have that ability. We already had that, so that was nice. The more tricky part is that you need to detect your devices connected to your OpenFlow domain. And this can also be done or is done by SDN controllers automatically. So whenever, for example, an ARP request or an ARP reply goes into the network, this packet is forwarded to the controller, and the controller learns about the device that is connected to a specific switch and a specific port on that switch. The problem here is that when you connect a device, a server, to one port, this controller learns about that device, and if the controller sees a packet on a different input port, it actually believes that the device has moved from one port to the other. Now, if you have link aggregations, you receive packets on various ports, right? And your controller actually thinks your device is constantly moving from one port to the other. It's funny to see that in a graphical user interface. It just hops from one port to the other. So you need to have a mechanism to deal with that, that your controller knows about. That's an aggregated link. I will see packets on different ports from the same source with the same MAC address. And then you have to do a lot of error handling, basically, because there are a lot of things that can go wrong. So ports can go down, then you need to evacuate your flows from that port and install it somewhere else. You need to make sure that you can detect your node correctly. However, every now and then you're not doing that. There can be scenarios where you don't where you misinterpret something and you have a false node detection. And you can also have human errors, configuration errors, so you can connect your link, your aggregated link configured at the host correctly to different ports on the switch where it's not configured correctly and stuff like that. So you need to handle that as well. So these are basically the challenges you need to address if you want to do that. And that's what we did. So we are using Floodlight for that. Actually, I intended to implement that for Open Daylight. However, Open Daylight turned in such a complex piece of software that there's basically no chance that my students will ever be able to work with it in time, right? So, I mean, if they're doing a master thesis of 6 months, they need like 3 months to get just to get used to Open Daylight, and then it's basically over. So we stepped back and used Floodlight again. This is easy to use. It's fairly easy to use and provides all the things we need to have. Moreover, we used Floodlight in the previous projects I was working at, and we had a lot of stuff that was already there. So that's the basic architecture of Floodlight. And what we, for example, already had was something like an ARP proxy, which basically filters out all the broadcast messages at the edges of your network. because you don't want any broadcast messages when you remove spanning tree. That's also what we did. We had multipath forwarding, so there's no spanning tree in our network anymore. A CLI configuration management and stuff like that. And now we modified also this device manager, which is actually, which contains all the device information regarding the hosts connected to your network. So the host or the device itself knows about its attachment points, meaning the switch port combination where it's connected to, and you need to adapt that with respect to your configuration of the aggregated link or the link aggregation group, so that Floodlight knows about that link aggregation group. So we can use, we have a configuration management to do that. We're using JSON. You can use anything else you like. You can use the CLI to do that. And in general, it's just that we can configure stuff there in a neat way, basically. We have this pathfinder, which calculates multiple paths from a source to a destination. You can configure that. You can have different algorithms to use to calculate these paths, for example, Dijkstra's or a modified version of that, or any graph theory algorithm you can think of and want to use. And then you can map new incoming flows to different paths, also based on an algorithm, for example, random or round robin, or you can think of something more intelligent to do. For example, at CERN we had a small application that provides additional information to the controller and then makes better decisions on which path to use from a source to a destination. Link aggregator is configured in the same way. You just provide an arbitrary name for your link aggregation group, and then you can configure ports that are actually a combination of the switch and the port your device is connected to, and multiple switch port combinations. And then you can also configure the algorithm that is used to map the flows to that various paths to these destinations. So what can we do with that once we implemented that, tested it, and it's working? That's more or less the same topology we had before. We have the two links going to one switch, which is not as high available as we want to use it. But now we have, But now this is not a standard network anymore with a distributed data plane, distributed control plane, but we have an SDN, so a software-defined network with a centralized control plane that takes care of everything, right? And using our link aggregation technique module that is implemented, we just can connect that switch, that host to any switch in that network. That's basically it. So it's nothing more, but that's increasing your their resiliency and stuff like that. If you want to have it even more secure, just add a second switch, a second link to a switch. So that's what we can do. You can connect your host to any switch in your OpenFlow domain. But it's getting even better, because depending on the controller or the algorithm that maps the flow, you can also have things like, okay, if there's another server connected to the right switch, it can directly go to, it can directly send data to that switch, to that host, right? Or so you can do a path selection based on your network topology, for example. So you can even improve the performance, or you can optimize your traffic management there. So the title of that talk was LACP meets SDN. So that was basically a static link aggregation configuration we can do What we actually intended to do, we are not really there yet, so we're still chasing some bugs, but the idea is basically to use the link aggregation control protocol, LACP, on the host. So you just need to configure LACP ports on your host, and then the LACP, the link aggregation control protocol, tells your network that it has a link aggregation group configured and sends all the information that is needed to your network. These packets are then forwarded to the controller, and the controller can take care of it, can use that information to actually configure itself or configure the network as such by itself. And that basically means you can, once this LACP is working correctly, this implementation for the SDN controller is working correctly, you don't need to configure anything in the network anymore to have aggregated links to servers. You just need to configure LACP port on your server. You need to set up the server anyway, so you just configure it there. You plug it to your network wherever you like, and it works. Okay, that brings me to the summary. So I introduced Kufstein a bit, again, if you want to collaborate, just let me know. And talked about the state-of-the-art link aggregation, how you can do it today with stacked switches and the pros and cons here. I explained the challenges for doing that, migrating that to an SDN, which is basically the device discovery. And I explained a little bit the advantages you have once you can do that with your with an SDN. That's it, and I'm happy to take questions.
Okay, there's one question over there. Thank you very much.
Pardon?
Thank you very much for your presentation. And now
welcome.
I saw. Yes, 2 questions, please.
So, have you tested this with only unicast traffic, or have you tested it also with multicast?
No, no multicast traffic. That's just, yeah.
Okay.
So, I mean, pardon?
Thank you. It's very cool. Thank you for your talk.
Thanks.
Hi. One of the things I like about classical LACP is that packets arrive in the order they were sent. I've not seen this formally defined, but the hashing algorithms mean that they have to go down every flow goes down the same leg of your aggregate. Is that going to be complicated by having an open flow fabric in there?
Sorry, can you repeat the beginning, because I didn't get it right?
I'm wondering if the open flow version of LACP can honor the packets arriving in the order they were sent that you get with LACP in classical.
Yes. So there's no packet. You mean if there's any packet reordering at some point? No.
Well, there isn't in old style LACP, but with OpenFlow, your packet filter, is it? I can't remember what you called it. But you just said round robin, and if the time it takes to traverse one link is longer than another, then your packets could arrive out of order.
Okay, so what LACP does in general, and also here, is it's per flow multipathing, basically, right? So one flow takes the same path over and over again. If there's another packet coming in from a different flow with a different flow characteristic, meaning the header fields, basically, then it goes a different. Then it can take a different path, but you won't see any packet reordering within one flow. And except for that, so for the different flows, you can set up any scheduling algorithm you like to have. So round robin was just an example. You can do it randomly, you can do it hash-based. You could even do it more intelligent, saying like ping goes that way all the time and TCP goes that way, UDP that way, or even based on ports, so that application takes that path all the time and stuff like that. That's possible.
Hi. How do you tackle the issue of having a TCP flow which its capacity is larger than one of the two links to transmit. For instance, if you have one flow of 11 gigs and you have 10 times 10 gigs, how is it possible to transmit this? And
Well, if I have
if you need to transmit a single flow
Yeah.
of 11 gigs, which needs 11 gigs
okay,
capacity.
there's no way doing that unless you split the flow into two flows, and then you can map it to different paths. But if it's one flow, it's congestion control, and then it goes down to 10 gig. So that's basically the work we did before with MPTCP. So if you have MPTCP running, multipath TCP, then it splits your flow automatically in the number of paths it can detect. And then even if it's from the application point of view, it's one single TCP stream. On the network, it's multiple TCP streams, and that increases the throughput.
So you rely on the application?
Pardon?
You rely on the application layer?
That would be, in that case, I would rely on the MPTCP layer. Yeah.
Thank you.
Do you know MLAG? MLAG, multi-chassis lagging.
Nope.
So I guess Juniper supports it.
Okay.
You span a lag across two chassis.
Okay. Yeah, I'm pretty sure you can find something else like that for Cisco. And
Yeah, Arista also does it. All the major ones do it.
The things we're doing are not necessarily completely new, right? You can do that. We did something else with when we removed VLANs, right? So we can have dynamic VLANs, and you can find solutions for that as well with Cisco. It's just cheaper, right? And it's also more flexible because it's open source. You can just adapt it to what you need, and you can have multiple vendors, switch vendors in your network. So it's not that you need the specific chassis from a specific vendor and to do that thing.
I understand,
Yeah.
and I think it's great.
Yeah.
So,
So that's the whole idea of doing these small exercises. Thanks.
Thank you. Is there any other question? If not, I thank again to Michal.
Thank you
If you
very
have another questions, please contact him,
Yeah,
or
by
you
the way.
can plan
So
a trip to Kufstein.
Yeah.
Okay, thank you very much.
Thank you.
So now let me invite the second speaker of this session. It's Katalin Merosku. He is a master researcher in Ericsson, where he drives research and innovation for the network management, for unified clouds and carrier network infrastructure, and he will give us an overview of the project Unify results. So, go on.
Good afternoon, ladies and gentlemen. I will be talking about opportunities for NRANs that could arise from activities that we do in the FP7 Unify project. And this is joint work together with my colleagues from Deutsche Telekom and the Swedish Institute of Computer Science. And we have to acknowledge also contributions from both my colleagues at Ericsson and from the co-authors of the NFVRG draft that is going to be mentioned in one of the slides. Okay. Let's see. Okay. We do it this way then. Okay, so here is an overview of my talk. I will be starting with a brief overview of the Unify project. Then I will explain what our concept of service provider DevOps means and what does it address. I will have a couple of examples of tools that are developed in the project and that you might find interesting. And then I will end the talk with some ideas on how some of these tools could potentially be integrated with the Persona framework. Good. So the Unify project, it's an integrated project. It's been started in November 2013. And it's a collaboration with a bunch of telecom operators like Deutsche Telekom and Telecom Italia and OT in Greece, industrial partners such as Ericsson and Intel, and a lot of universities and research centers in both Sweden and Germany, but also in Hungary and in Italy and in Spain. So we are a little bit all across the continent. The aim of the project is to increase the velocity of telecom services, so increase the velocity of telecom service introduction. And the way we do this, it's by developing a unified programming abstraction for both network and cloud resources that is based on a unified orchestration engine and a generic processing. And I'll have a little bit of more details on how is this actually done in the project. In the work package that handles management tasks and on that I'm representing here, we develop a novel observability and verification features that apply to software-defined infrastructure. So this is an overall view of the components that are being developed in the Unified project. And I will start from the, I will start from the lower level of the infrastructure on the lower left corner with what we call a universal node. And the universal node, it's a set of programmable resources that include both compute and network and storage resources. You can consider a universal node like a fairly big server that has a lot of CPUs, a lot of storage, a lot of network capacity. This server has a local orchestrator that manages these resources, and then in the Unify project in the work package 3 that deals with the orchestration, we define several layers of recursive orchestration that further abstract the resources from the lower layers in the infrastructure nodes, such as the programmable node that would be positioned here in the infrastructure, all the way up to an end user or an enterprise user that asks for a service from a telecom provider. Going to how operations are done today in networks. When we look at configuration management and application deployment, a lot of the tasks are actually done using tools such as Chef. This is really nice. People like it because it runs on a central server. Clients are deployed on each resource that is to be managed, either a switch or a router. There is a lot of scripts that can be produced in order to automate tasks. And they are written in languages which are very familiar to the people that do both development and operations of network, such as Ruby. And it also allows for basic monitoring of resource parameter attributes in addition to simply configuring resources. On the performance management side, we have tools like AppDynamics and New Relic that are targeting monitoring and analytics. And they are very nice because they monitor both server and application performance. They have very nice user interfaces plotting a lot of pretty graphs for the operations people to see or for the developers to see. There's even the possibility to vary the level of details that is presented in the graphs depending on the role of the person. So that's quite nice. They provide some correlation between the performance of application and the performance of the infrastructure. And they allow for building new plugins that allow collecting new types of data also in languages that are familiar to a lot of people. So what's the downside? with using these tools? Well, when it comes to the chef-style configuration management, scripts don't scale very well. After a while, operating large quantities of infrastructure, you end up with a lot of scripts, and then it's very hard to identify cross-script dependencies, and it's difficult to discover new resources, which, by the way, when we talk about cloud orchestration, VMs can be created at any given time, so it's difficult to integrate that with a cloud orchestration. Then, on the monitoring and analytics side, both AppDynamics and New Relic, they are aimed at enterprise applications. Carrier infrastructure, it's not that easy to integrate. It's different types of standards. Not all these standards are public, so some of the information is manufacturer specific, and that's not easy to be accessed. And then it also is not connected, so these tools are difficult to connect to orchestration and controllers, which may lead to configuration inconsistency for the probes. Okay. Right. In Unify, we looked at DevOps principles that were introduced by IBM some years ago. And IBM, what they were trying to do is to formalize a little bit bits related to the DevOps movement. And they define these 4 principles: deploy repeatable, reliable processes, develop and test against production-like systems, monitor and validate operational quality, and amplify feedback loops. Now, we looked in the project on how we can take this from a data center context and apply these principles to a carrier network infrastructure. And we defined 3 roles for the people that would interact with the software-defined infrastructure. The role of a software developer, the role of a service developer, and this is the person that assembles a service from predefined blocks using either a graphical user interface or a set of scripting templates. The operator is the role that does the daily operation of the network. In data center, this is very much service reliability engineering. And then we have a very specific role, which we call the virtual network function developer, and these are software developers that develop network functions that are going to be part of the infrastructure and need to be operated with the infrastructure. When we looked on how on what we need to do in order to apply these principles to software-defined infrastructure, taking into account the roles, we concluded that we need to have processes that are the same and available for all these roles in the infrastructure, and visibility of who did when, did what at what time. We need isolation properties in the infrastructure, and we need to be able to allow for frequent customizations, which means downloading new virtual network functions at any time in the network. And we need to establish a procedure for validating new services that are introduced. So, for example, we need to generalize Y1564, which was defined for Ethernet services. And something that we don't address in the project is the amplifying feedback loops between the developers and operators, because this is something that is very much culture related, and we are technical people. There's no time, unfortunately, in the project to do that. In terms of requirements for DevOps in telecom operator networks, we see still a requirement for 5.9 service availability, not for the lower layer infrastructure, but for the service availability. And this is tougher compared to the data center, and it requires an increased network stability. We also see that latency and delays in telecom operator networks, when we take into account all the access part of the network, they have a different impact on partitioning properties of protocols due to the spatial distribution of resources. When it comes to observability, we need increased granularity and scalability to millions and millions of continuous customer sessions along that infrastructure. And we need flexibility to adapt to resource programmability for a multitude of protocols. It's not only one type of protocol that is being transmitted on those networks. For the validation and verification, we would very much like to extend standards such as the Y1564 to new types of resources and service classes, because we think that that's a very good general process to measure and validate quality. And for the troubleshooting, well, there is a plethora of individual tools that solve very specific problems for one technology, but make it extremely difficult to use them in an integrated manner. So we need a common API for these tools. When we look at the NRANs compared to the telecom operators that are involved in the Unify project, what we see is the NRANs have much smaller and much more agile teams. We see that the infrastructure is more geographically concentrated. There is no such a wide access network as in Deutsche Telekom or Telecom Italia with all the wireless base stations. We see a high degree of interaction with the customers and integration of customer demands in the services which are offered by the infrastructure. And we see inherent willingness to support users experimenting with the infrastructure. And this is very similar to our VNF developers. Now, as part of the service provider DevOps in Unify, we took the architecture with all the orchestration, resource orchestration layer and service orchestration layer and the infrastructure controller that are in the background here. And we put the roles that we defined for the VNF developer, the service developer, and the operator. And we looked at how can we help these roles from a monitoring and verification perspective. And in my presentation today, I will focus on the monitoring side. So what we need is we need to integrate the monitoring capabilities with the resource and the service orchestration. And for that, we are developing a language which we call Measure that would annotate a network function forwarding graphs, which are resource representations at the service layer and at the recursive infrastructure layers. And this language defines what and how to monitor in terms of KPIs. And it also supports triggers. So the orchestration can be told to scale up or scale down the use of resources based on KPIs expressed in this language and pushed as annotations to the resource graph. And at the very lower layers of the software-defined infrastructure, we are defining a set of monitoring functions that solve very precise problems, which are SDN-specific in a novel way. And we are defining a monitoring bus that allows these functions to make available a lot of information to the orchestration layers in a very scalable way. So what we end up with is a scalable software-defined monitoring and verification set of capabilities available at the infrastructure layers with a common interface that allow the orchestration layers or any other type of consumers to have a very efficient data retrieval from the infrastructure observations. Okay. Right. So now I will have two examples of tools that are developed in the project. And I will start with an example that I'm working on at Ericsson. One problem with OpenFlow is that when we have aggregate flow descriptors, there are tens of hundreds or thousands of flows that can be hiding behind one of these aggregated flow descriptors. And we would like to be able to estimate how many packets are lost in one of these flows. Now, it's not straightforward to use any of the MPLS or Ethernet OEM tools that were defined by either IEEE or the IETF for this. So we had to define our own functionality. And the way we've done it is to define a set of tables that are able to create flow descriptors by themselves within certain limits specified by a policy from the controller, inform the controller of the arrival of a good candidate flow, then the controller takes a decision whether to use that or not for calculating packet loss, and if so, it will install a rule in the egress part of that flow. And then we can do the packet flow calculation. It's, of course, a little bit more complex than I'm summarizing it right now, but we don't have really the time in this presentation to go into the details. I'll be happy to talk to you afterwards if there are questions with respect to that. One of the advantages of this method is that we are not inserting any probes into the network infrastructure. We are using the traffic that the user is generating anyway. And also we are using for communication messages which are automatically generated by the OpenFlow protocol when flows expire, for example. We are implementing this in the Open Daylight controller and Open vSwitch, and the implementation is ongoing. And I would conclude, I would agree with the previous speaker that it's not straightforward. The second example of a link utilization, of a monitoring function that we have, it's a link utilization monitor. And this is a function that uses two counters on each of the ports, on a network port, to determine the risk of very short-term congestion. Each of the counters represent either the first or the second statistical moment for that link utilization. And we transmit only an estimate to the controller instead of a very high-speed data flow. So if you imagine, we can monitor, we can get very good estimates of this short-term congestion by monitoring the port every 3 seconds. And the resolution that we get, it's equivalent to running SNMP probing on that port at a millisecond interval. So overall, with this method, which is developed by my colleagues at SIX, we get thousands of times rate reductions compared to standard SNMP or reading those counters, the flow counters directly through OpenFlow. And here is just a little bit of data to show that, yeah, it works. This is a trace on a 10 gigabit link from an operator in Sweden. And for the 0.3 seconds intervals, then we have a number of very good hits and very few misses of the micro congestions events on that link. Regarding this slide, it's really good. It's a very good example of being at the Terena conference and learning things. Because when I left Stockholm, the deployment in the Jean testbed service said deployment in the Jean OpenFlow facility But you come here, you learn something, and you have the opportunity to change your slides. So that's really great. So the assumption for integrating our work with Perf is that we could deploy a slice in the Géant testbed service with switches that have our measurement capabilities. So OpenV switches that have either the 2 counters or the table capabilities that we have for our 2 different methods. And we can integrate either with a Perf user interface, giving SDN congestion or packet loss metrics, or we can give automation generation, an automated generation of alerts through the northbound interface of the Open Daylight controller onto the Perf interface. We can also consider an integration based on the Perf protocol for message exchange between the components. And in this case, we would use the Unify monitoring tools as another category of interface statistics. And this would translate the Unify REST API onto the RRDMA of the Perf framework. So in conclusion, the Unify project proposes new ways of adopting DevOps principles in operator networks and is building a set of tools along these principles. The tools that we develop could provide additional performance information with very low overhead on both the data plane and the control plane of the infrastructure. And this is actually an idea that was suggested to us by one of the reviewers of our TNC presentation proposal to run a survey on DevOps tools and practices. We have started this. We have managed to get support from SIGNOC for sending a message and asking people to give us their input. We've not been very successful as a result of that message. But if there are people here that are willing to help and that would look at experimenting with our tools in like November framework, when we will have a lot of them made public as open source, then just help us by answering some questions in the survey. This is about what type of interfaces you'd like to see in those tools for easier integration into your processes. And that is it. Thank you.
Thank you, Katalin. Before question from the audience, I have one dealing with the project. The project is running or it's closed already?
The project is running and it will finish at the end of April next year. So the project is still ongoing. We have almost a year.
Okay, thank you. And now time for the question. We have another time for a few questions. Is there any? If not, so thank you again.
Okay, thank you.
So, and let me invite the third speaker. It's Yanis Mitsos. He is coordinator and supervisor of operation and service provision from GRNet, and his presentation will be about monitoring of VPNs. So, please.
Thank you, Helmut. Thank you very much. So, good afternoon. My name is Yanis Mitsos. I work for the Network Operations Center of GRNet. I'm here to present you a work that has been carried out from my department, which aims at providing an automated way of including OAM capabilities in our carrier network. Just a few introductory slides. We are running the 4th iteration of our network, which is called GRNet 4. The major difference compared to the previous networks is the fact that all the bullets that you see in this map are now routers, so no more switches exist at the backbone. I will come back to this later on. So it's a carrier network. We have points of presence all around the country, a lot of points to be, let's say, operated. And among them, there are 2 routers in the capital of Greece, in Athens, which serve the layer 3 needs of our customers. The heart of the network is the carrier network. It's a transport network using MPLS. It offers services to the customers, as you see here. We have 2 types of customer, mainly. The ones that require only layer 3 connectivity services. Therefore, in most of the cases, we avoid putting a CPE at their premises, where there are many other customers who need a lot of services like layer 2 VPNs, VPLS, etc., and therefore we put CPEs, access switches into their premises in order to monitor and monitor their offered services, and also to give diversity according to their needs. Last but not least, the carrier network interoperates with an IP network, the previous 2 routers that I mentioned before, and we have at the moment 2 data centers offering cloud services. Soon will be extended to 3 more. What is important to be mentioned here is that it's of course a layer 3 collapsed architecture. You see only 2 routers, 2 actually layer 3 routers. All offered services are given on top of VPNs. So if one customer wants to have layer 3 connectivity, its BGP will be established on top of a layer 2 VPN that connects the end user with our IP router. As you can understand, we have a lot of VPNs at the moment running, more than 400, because all of our services are delivered on top of them. And you can easily understand what is the problem. The problem is that having all those layer 2 services, it's very difficult to have an insight into different things. You don't have access to a quantitative and qualitative, let's say, measurements. You cannot monitor easily a layer 2 VPN. It's not so easy. And you cannot have graphs. You cannot have quantitative measurements like delay, jitter, etc., etc. So this is the problem that we decided to, that's the problem that we need to solve. And in order to address this, we created, let's say, a troika. Sorry, I was not supposed to say this. A team of 3 persons, a network engineer, system engineer, and developer, who sat together and came up with this, those 2 statements, namely that we need somehow to introduce service continuity and service continuity, let's say, functionality, and performance monitoring. There is, though, a small problem that we have 400 VPNs already out there, and it would take a lot of work in order to go traverse all these routers and enable OAM capabilities. Having said that, our, let's say, motto and, let's say, the way that we work is trying to automate things. So we spend a lot of time in designing things, testing things, automating things, and we prefer just sitting relaxed and watching the monitoring tools doing the job for us. Before I enter too much into details, there are a few slides about theory, about OAM, and won't go too much into the details. There are 2 big umbrellas, 2 big families, if you wish. It is well known that ITUT and ITF are not let's say, working so efficiently together. Initially, ITF created the protocol 802.18g, which tackles mostly the connectivity fault management, let's say, aspects, while ITUT has been addressing performance aspects. In most of the vendors, both families are enabled, so it's not something new. You can have the functionality that you wish, and most of the time it's hidden. You don't know which implementation of those 2 is offered. A few words about CFM. So it's a family of protocols, as I mentioned, which takes care of the monitoring and detection of end-to-end, let's say, of end-to-end continuity, let's say, services. Those frames, those PDUs, are injected into the typical circuits, the customer circuits, and traverse the links. And there are 3 key keywords that you need to have in mind. The maintenance points. These are the points that you would like to take measurements. It could be either your measurement points or it could be your customer's measurement points. Those two measurement points define a maintenance domain. And the maintenance domain normally has a number, an index from 1 to 7. The bigger the number, the outmost maintenance domain is indicated. So for instance, maintenance domain number 7 indicates that you monitor the whole link, so from the customer to the end, to the other end. And there is a maintenance associations that actually maps the service instances for the specific maintenance domain. On the other hand, ITU Y1731 provides, let's say, the specifications for performance management. You have two major, let's say, categories, the frame delays and the jitter, the delay variation. In our case, we have decided to run only two-way measurements. There are some technical concerns here. I can explain to you later if you wish. And this picture provides an overview of what we do, of what we measure actually. So this is a PE router close to the access switch of our customer. We measure from this point, namely from the interface that faces the customer, it's the customer-facing interface, up to the other end interface. So this is a maintenance domain which has nominated the number 5 in order to give us the option, if we wish later, to include another, to extend this maintenance domain, include a maintenance domain number 7 for our customers, to have end-to-end measurements. The maintenance association monitors the connectivity of the layer 2 VPNs, as I mentioned before. We have layer 2 we have VPLS service as well. We have IP service as well. We don't measure them at the moment. We measure only the layer 2 VPNs. So a few things about the implementation. What are the tools being used? The first thing and the foremost is a VPN database. We built this initially when we started deploying the VPNs. It's a custom, it's homegrown, let's say, application. It doesn't actually create the VPNs, it creates only the configuration. So someone has to manually then put the configuration to the routers. And it's also important to underline here that this is it's not an application that is offered to our customers. So it's only for our internal use. Nevertheless, what you need to keep in mind here is the fact that we have a central database that is up-to-date. It fetches all the time information from the routers and maintains a consistent view of the VPNs that are implemented in our network. Netconf, the ones of you who operate routers are aware of this. It's a protocol, it's an XML RPC, a way of getting information, getting configuration, implementing, let's say, configuration, getting measurements from the routers in a consistent way, not like the old days with all those old-fashioned expect, let's say, statements and old tools. The application that has been developed it's based on Python and Django for the Django framework. There is no UI though; it's just an application. We use the RRD toolset in order to graph. And last but not least, Isinga is a tool, an alarm tool that has been massively used by the servers team and from the routers team in order to, let's say, run active checks for our infrastructure. So the first thing, when a new VPN is configured, the tool periodically traverses all the routers using netconf, downloads, fetches the configuration of the VPNs, and if a new VPN is identified, then it automatically creates the corresponding configuration in order to put OAM capabilities for this VPN. This configuration is pushed to the routers, and there is a reporting message to the members, to the operation team, saying that we have identified the new, let's say, VPN configuration has been pushed successfully, and now we measure this VPN. The second thing is we need somehow to create automatically, based on this data, the single configuration. The application fetches details from the database, from the VPN database, and creates the appropriate configuration that is being advertised to Isinga. So Isinga periodically polls the application in order to understand if there are new VPNs and new measurement points in our network. Later on, the same application is again traversing all the routers. It fetches information from the routers. Actually, it performs CFM checks with netconf in order to get the state of its VPN. And at the same time, it pushes the results to Isinga, using a protocol that is called an Agios system check, something like that. So whenever a new alarm is identified by the application, it's been pushed to Isinga, and Isinga has a nice view. I will show you to you later on, in order to report a problem. The quality measurements graphs, the OAM application builds the RRD file. So whenever a new VPN is created, a new RRD dataset is created, and the application itself also creates the PNG, the image, the actual image, which is being later on presented by other tools. Again, we measure two-way delays and two-way jitter. As I mentioned before, we have a small technical problem, which is, according to our vendor, the configuration that we use is not very well supported for one-way delays measurements and jitter measurements. And the fact is that the problem is actually focused on the fact that we have LACP aggregated interfaces connecting the VPN handoff routers to the IP actually routers, and Juniper does not support measurements on top of aggregated interfaces. This is an overview, publicly available, of course. This is the monitoring tool that is being deployed internally. It provides monitoring statistics for our customers. You can see the tabs here that a new tab has been inserted, the one which is related to the OAM. And what you can see here are from a specific router, the delays and the jitter, the variation. With regard to CFM again, the routers themselves initiate every 1 second a frame, the center frame between those two measurement points in order to verify the service continuity. We fetch those data and we present them, as I told you before, with a mechanism that I have described into Isinga. So this is a typical, let's say, overview of Isinga. You can see that those VPNs are marked with green, which means that they are operating as expected. This concludes more or less my presentation, short presentation. The code is open source. It's GPL version 3, if I recall correctly. Most of the code is, as I mentioned before, relies on open source tools. The only thing that is proprietary according to our implementation is the VPN tool, namely a database that holds and maintains the information about the VPNs. A part of it You can get it from GitHub, you can use it, you can test it.
Thank you very much, Mitsos, for the overview of your own development for this tool. I am asking you for the question. Is there any for Mitsos? Or some comment?
So whether it was too good or too bad?
One.
Martin.
Sorry, am I right? You're using Ethernet over MPLS simply to serve all the connections? All those VPNs are just EO MPLS or what?
Okay, let me go back.
Yeah.
So as I mentioned before, this is the core of our network. So in all these points of presence, we have routers, Juniper MX routers.
Yeah.
We don't have switches anymore. All the services that we offer to our clients rely on a VPN service.
But why?
Because you want to have diversity. You want to offer diversity to your customers. So you don't care if they're going to use, if they want to implement, let's say, a layer 3 link, or if they would like to implement a VPLS. So you have a carrier network that carries, transfers packets, frames packets, and it's up to them to decide. It's a more flexible way instead of having the typical layer 3, let's say, topology.
Okay. Okay.
Hi, thank you for your presentation. I was wondering, how do you coordinate which device gets which map ID so that they stay unique?
Sorry, which?
Measurement endpoint ID. It has to be unique for each maintenance association. How do you make sure it is unique? Are they all just small domains? Or is it one big domain with many endpoints?
No. Yes, it's a big domain. It's a huge domain which has all the instances, all the VPN instances within it.
Yeah. Okay. So how do you define
we have
unique addresses?
I'm not sure if it's clear here. In our VPNs, we have a unique, let's say, UID, something like that, which is also maintained in the database, and this is used. It's a unique hashtag that, let's say, identifies the VPN. So this is used, that's why I mentioned before, it is here. So what you see here, it's a description of interface of a layer 2 VPN, which says that it's a VPN from one customer at this side to the other side. And here you see that we have a UUID, if you wish, a unique identifier. So we maintain this in the database and we know each VPN, what serves actually.
Thank you.
What is the typical full width, half max of your jitter?
What is the typical, sorry?
What is the typical full width, half maximum of your jitter histograms?
I don't know. I have to go through the graphs. I'm not sure. I cannot answer you right now. We can sit together and see the graphs, I mean, if you wish.
So, if there is any other question, thank you, Yanis, again. So let me thank all of speakers of this session because we save a lot of time. If you want to ask any of them now, you can. No question. It seems we all are tired because the conference is near its end. So before I let you go to break for some refreshment, let me announce some things. I have notes here. So the first is tonight is the gala dinner. The buses will start from the pier at 7 p.m. and 14 minutes, and go back starting at 10 p.m. So if you need some additional ticket for this, please you can buy it. So the morning session will start half an hour later, and there will be coffee and tea for you prepared. I have to say also, in this building is a presidential car museum, and there is free for you. You can visit it and look at the car of the Portuguese president. So, and before I let you go to the break, you have to promise me that you will visit the demonstration and meet the poster session. That it's all from me. No, but don't remember to put the feedback of this session to the system. So it's all from me. Thank you very much and have a break.